The universe began as a seething ocean of raw energy. In that first blinding flash, everything we know was forged, but the recipe remains a profound mystery. What were the very first building blocks of everything we see? How did the simplest elements, hydrogen and helium, come to be? This is the story of Big Bang Nucleosynthesis, the cosmic alchemy of the first 3 minutes. Yet for all its success, the standard model leaves puzzles unsolved, like a missing ingredient in a primordial soup. Today, we will explore 30 fascinating theories that attempt to explain the precise details of our universe's first light elements. By the end, you will understand not just what happened, but how the very first seconds of existence continue to challenge our deepest laws of physics. We will question if the early universe was smooth or lumpy, if dark matter particles cooked the first elements, and if the laws of nature themselves might have been different. What do you think is the most surprising ingredient in the recipe for reality? The clock starts at a temperature of over 10 billion degrees. For the first second, the universe is too hot for anything to form. It is a chaotic broth of fundamental particles, quarks and electrons and photons, all constantly colliding and being ripped apart. But as the cosmos expands, it cools at an astonishing rate. By the time 1 second has passed, the temperature has already plummeted to around 1 billion degrees. This is the moment conditions become just right for the first permanent structures to emerge. Protons and neutrons, which are themselves made of quarks, can now survive without being instantly destroyed. The stage is set for the first and most important act of cosmic construction, the forging of the lightest atomic nuclei. This process is called Big Bang Nucleosynthesis, and it is the cornerstone of our understanding. It all happens in a breathtakingly short window, from about 1 second to roughly 3 minutes after the beginning. In that time, the universe goes from a soup of individual particles to a place where the first seeds of matter have taken root. The first step is the simplest fusion. A single proton, which is a hydrogen nucleus, and a neutron bind together to form deuterium, a heavy form of hydrogen. This is a fragile bond, and in the early chaos, deuterium nuclei are constantly being smashed apart by high-energy photons. For a brief period, there is a stalemate, a balance between creation and destruction, but the expansion does not stop. The universe continues to cool and thin out. At the 2-minute mark, the photon energy drops just enough. Deuterium nuclei can now survive. This is the bottleneck that breaks. Once deuterium is stable, a cascade of reactions begins. Deuterium quickly fuses with another proton or neutron to form helium-3, a light isotope of helium. 2 helium-3 nuclei can then collide to create a stable helium-4 nucleus, releasing 2 protons back into the mix. This entire chain reaction from proton to helium is the primary engine of the first 3 minutes. It is a frantic, universe-wide race against the cooling clock. The model makes incredibly precise predictions. It tells us that about 25% of the ordinary matter in the universe by mass should have ended up as helium-4. The remaining 75% stayed as simple hydrogen, single protons. It also predicts tiny, trace amounts of the other light elements, deuterium, helium-3, and lithium-7. These are not just rough estimates, they are specific numbers calculated from the known laws of nuclear physics and the density of the early universe. For decades, astronomers have looked out into the oldest corners of the cosmos, studying pristine clouds of gas that have never been inside stars. What they find is a match that is nothing short of miraculous. The observed abundances of these light elements align almost perfectly with the predictions of Big Bang nucleosynthesis. This agreement is one of the strongest pillars supporting the entire Big Bang theory. It tells us our basic understanding of those first few minutes is fundamentally correct. We have deciphered the universe's first recipe. Yet, a perfect match in science is often where the deepest mysteries begin. The model works flawlessly only if the conditions were just so. What if something was stirring the pot? What if an unseen player was present in that primordial kitchen, subtly altering the yields? The success of the standard model is so profound that even the smallest deviations from its predictions become glaring clues, pointing toward physics we have yet to discover. But that near-perfect match holds a single, stubborn crack. The amount of lithium-7 we see in the oldest stars is about 3 times lower than the pristine Big Bang calculations predict. This is known as the lithium problem, and it is a small discrepancy with enormous implications. It suggests our picture of the universe's first 3 minutes might be missing a crucial detail. One compelling idea challenges a fundamental assumption of the standard model, the idea of a perfectly smooth beginning. This is the inhomogeneous Big Bang model. What if the infant universe was not a uniform soup but was instead lumpy, filled with pockets of slightly higher and lower density? These lumps would not be galaxies, not yet. They would be microscopic variations, seeds sown by the same quantum fluctuations that would later grow into the vast cosmic web of galaxies. In a perfectly smooth universe, every proton and neutron experiences the same temperature and density, leading to a very predictable set of nuclear reactions. But introduce lumps and everything changes. Imagine 2 adjacent kitchens trying to bake the same cake. One kitchen is hotter and has more flour, the other is cooler with less. Even with the same recipe, the results will be different. In a lumpy early universe, regions of higher density would have packed more protons and neutrons into a tighter space. Nuclear reactions in these hot, dense pockets would have run faster and more efficiently, burning through the available fuel differently. Crucially, the pathway to creating lithium-7 is delicate. It relies on a specific chain of reactions involving helium-4 and tritium, a heavy form of hydrogen. In a smoother cosmos, this chain produces a predictable amount of lithium. But in a lumpy one, the story changes. In those overstuffed dense regions, the frantic nuclear reactions might have bypassed the lithium-making pathway entirely, or more likely, they could have produced beryllium-7, an unstable element that decays into lithium-7 over time. If these dense regions were then mixed with cooler, emptier voids before the lithium could fully form, the final average abundance of lithium across the whole universe could be significantly lower. This theory elegantly connects 2 great chapters of cosmic history. The same quantum seeds that dictated the large-scale structure of the universe, the galaxies and clusters we see today, may have also left their fingerprint on the very first atoms. It suggests that the blueprint for everything, from the largest supercluster to the lightest element, was written in the same instant of chaotic quantum birth. The lithium problem, then, is not just a puzzle about a trace element. It is a potential window into the texture of the newborn cosmos, a hint that the universe's first moments were far more turbulent and interesting than a perfectly smooth soup. Another possibility is that the cosmic kitchen had an unexpected guest. The decaying particle theory proposes that alongside the familiar protons and neutrons, the early universe was also populated by exotic, massive particles left over from an even hotter, denser era. These particles would have been unstable, living just long enough to witness the drama of Big Bang nucleosynthesis before vanishing. Their decay, however, could have thrown a wrench into the delicate nuclear machinery. Imagine you are carefully measuring ingredients for a cake when someone walks by and accidentally bumps the table. A little extra flour spills into the bowl, changing the final texture of the entire batch. In the cosmic kitchen, these exotic particles would have acted like that bump. As they decayed, they could have released a flood of high-energy photons or injected a surge of extra neutrons into the mix. This would have had a profound effect on a single critical number, the neutron-to-proton ratio. This ratio is the master control knob for how much helium gets made. Helium-4 requires 2 protons and 2 neutrons. If you have more neutrons available, you make more helium. In the Standard Model, this ratio is set by the universe's expansion and cooling, freezing in just before nucleosynthesis begins. But if a swarm of decaying particles suddenly dumped a fresh batch of neutrons into the soup after that freeze-out point, the balance would be disrupted. The neutron-to-proton ratio would jump, and the nuclear reactions would produce significantly more helium-4 than the Standard Model predicts. This creates a fascinating tension. We know from observations that the helium abundance is very close to the predicted 25%. So if this theory is correct, then the decay must have been exquisitely timed, or its effects precisely counterbalanced by something else to keep the final result so neatly in line. This is where the theory connects to one of the greatest mysteries in modern physics, dark matter. Many leading candidates for dark matter, like particles known as weakly interacting massive particles or WIMP, would have been produced in the fiery early universe. They are thought to be stable, which is why they persist today as the invisible scaffolding of galaxies. But what if some of their heavier cousins were not stable? What if they decayed away into radiation and ordinary particles during those first few minutes? The light elements we see today, especially that precise amount of helium and the puzzling shortage of lithium, could be the fossilized imprint of those long-dead particles. In this view, the recipe for hydrogen and helium is not just a story of protons and neutrons, but a cryptic message from the dark sector of physics. The first atoms are a ledger, recording interactions with a hidden world that shaped the cosmos before fading from view. Neutrinos are the universe's most elusive particles, ghostly travelers that pass through entire planets as if they were empty space. In the first few seconds, however, they were anything but passive spectators. They dominated the energy density of the cosmos, and their behavior was the engine driving its expansion. The neutrino asymmetry theory suggests this ghostly population held a hidden imbalance. What if there were significantly more neutrinos than their antimatter counterparts, anti-neutrinos? This imbalance, a lepton asymmetry, would have been a silent but powerful force. In that dense early soup, neutrinos interacted constantly with everything else. An excess of them would have effectively pumped more energy into the expansion, causing the universe to cool and thin out just a little bit faster. Think of a pot of water boiling on a stove. If you turn up the heat, the water boils more vigorously and the steam fills the room faster. A neutrino asymmetry would have been like turning up the cosmic heat, making the universe's expansion more vigorous during those critical first minutes. This slight change in timing would have had a direct impact on the nuclear assembly line. A faster expansion means the temperature drops below the threshold for nuclear fusion sooner. The delicate chain reactions that build deuterium, helium, and lithium have less time to run their course before the universe becomes too cold and diffuse for them to continue. The yields of every element would shift. Most notably, with less time available, less lithium-7 would be synthesized, potentially explaining the observed shortfall. But this theory reaches far beyond a single element's abundance. It connects directly to one of the most profound questions in all of science: why does anything exist at all? According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate in a flash of pure energy. If perfect symmetry had been the rule, every particle should have found its opposite, and the universe would be nothing but a fading sea of light. The fact that we live in a cosmos made of matter, with stars, planets, and people, is proof that this symmetry was broken. Somewhere, somehow, a tiny excess of matter over antimatter survived the Great Annihilation. This is the Baryon asymmetry, the reason protons and neutrons exist. The neutrino asymmetry theory proposes a parallel story, a lepton asymmetry. It suggests the imbalance might not have been confined to the particles that make up our atoms. It could have also existed in the ghostly neutrino sector, a hidden mirror to the visible matter imbalance we see today. In this view, the lithium abundance is not just a nuclear physics puzzle. It is a possible echo from the moment the universe decided to favor existence over nothingness. The recipe for the first elements may have been written by the same unknown law that allowed anything at all to remain. This leads us to a theory that questions the bedrock of reality itself. The constants of nature, like the speed of light or the strength of gravity, are the fixed rules of our cosmic game. We assume they have always been the same, unchanging from the first instant to today. But what if that assumption is wrong? The variable constants theory dares to suggest that in the extreme heat and density of the newborn cosmos, the rules themselves might have been different. Imagine trying to bake a cake, but the oven's temperature dial is not calibrated, or the meaning of a cup of flour subtly changes halfway through the recipe. The final result would be unpredictable. In the cosmic kitchen, the most critical dial is the strong nuclear force. This is the glue that binds protons and neutrons together inside an atomic nucleus. Its strength determines how readily particles stick and how much energy is released when they do. In the standard model of Big Bang Nucleosynthesis, this force has a very specific, unchanging value. It allows deuterium to form at just the right temperature, and it dictates how efficiently protons and neutrons fuse into helium. But let us tweak that dial just a fraction of a percent. If the strong force were slightly weaker in the early universe, the bond holding a deuterium nucleus together would be more fragile. That crucial bottleneck, the moment deuterium becomes stable, would happen later. The universe would have cooled and expanded more before the nuclear chain reaction could truly begin. With less time and a thinner soup, far fewer reactions would occur. The yield of helium-4 would plummet. Conversely, if the strong force was slightly stronger, deuterium would form much more easily and earlier. The nuclear fires would ignite with a fury, burning through the available fuel rapidly. Nearly every neutron would be captured, leading to a universe with a much higher abundance of helium, perhaps even approaching 40 or 50% of all ordinary matter. Our observations show neither of these extremes. The helium abundance is pinned at that precise 25%, a number that perfectly matches the predictions using our current constant values. This is a powerful argument for stability, yet the mere possibility of variation opens a profound line of inquiry. It forces us to ask why the constants have the values they do. Are they truly arbitrary, or are they the only values that allow for a universe complex enough to eventually ask such questions? Some theories, like certain models of string theory, actually predict that what we see as constants may be the frozen results of fields that settled into their current values as the universe cooled. A tiny, early variation could have left its signature in the primordial element abundances. So while the observed helium seems to lock the constants in place, scientists continue to test this foundation by looking at the most distant quasars and the oldest light, searching for any whisper of change across cosmic time. The recipe for the first elements, therefore, is not just a test of nuclear physics. It is a stress test for the immutable laws of the cosmos. Magnetic fields weave through the cosmos today, guiding the formation of stars and shaping entire galaxies. But their origin story might reach back to the universe's very first moments. This theory proposes that powerful magnetic fields were born in that initial chaos, and they were present in the kitchen during the cooking of the first elements. These are not the familiar fields generated by moving charges in stars. They would be primordial, sewn into the fabric of space-time itself by violent processes like phase transitions in the early universe, moments when the fundamental forces split from one another. Their presence would have introduced a new and strange ingredient into the nuclear soup. A strong magnetic field does something profound to charged particles. It forces them to move in spirals, corkscrewing along the field lines instead of traveling in straight paths. In the dense plasma of the first few minutes, this altered motion would have changed how often protons and other nuclei collided. The rates of the very fusion reactions that built hydrogen into helium are governed by these collision probabilities. A pervasive magnetic field could have effectively focused the particles, making some interactions more likely and others less so, subtly shifting the final yields of deuterium, helium, and lithium. More intriguingly, such a field would not have been perfectly uniform. It could have created pockets or anisotropies where the nuclear reactions proceeded at slightly different speeds. One region aligned with stronger field lines might have produced a bit more helium. Another region in a magnetic trough might have lagged behind. The universe's first elements might not have been mixed as evenly as we assume, bearing a faint, fossilized imprint of this primordial magnetism. This idea offers a potential pathway to addressing the lithium problem. The delicate reactions that create lithium-7 are especially sensitive to the environment. A tangled web of magnetic fields could have disrupted these specific chains, perhaps by scattering the key particles before they could fuse, leading to an overall lower abundance in the final tally. The most tantalizing part is that this theory might leave a detectable signature, not in ancient stars, but in the oldest light we can see, the cosmic microwave background. This afterglow from the universe's infancy carries patterns of hot and cold spots. A primordial magnetic field would have left a unique fingerprint on that pattern, a specific kind of distortion in the polarization of that light. Astronomers are actively searching for this signal. Finding it would do more than solve a puzzle about lithium. It would open a direct window into the universe when it was less than a second old, revealing a time of unimaginable energy when the very forces of nature were taking their modern form. The first atoms, then, could be more than nuclear ash. They might be the silent witnesses to the birth of cosmic magnetism. Before protons and neutrons could even form, the universe was in a far stranger state. For the first millionth of a second, temperatures were so unimaginably high that the fundamental building blocks of matter could not bind together. This was the era of the quark-gluon plasma, a primordial soup where quarks and the gluons that glue them together roamed freely, unconfined. It was a state of matter so exotic that physicists now recreate fleeting glimpses of it in powerful particle colliders. Then, as the universe expanded and cooled past a critical threshold, a monumental phase change occurred, like steam condensing into water. Quarks and gluons suddenly froze into composite particles, the first protons and neutrons. This transition, known as confinement, set the stage for everything that followed. But what if this freezing was not perfectly uniform? Think of a lake freezing over on a cold night. The ice does not form a perfectly smooth, flawless sheet. It develops cracks, bubbles, and regions of different thickness due to tiny variations in temperature, wind, and impurities in the water. The quark-gluon plasma likely had its own impurities and fluctuations. Theorists propose that as this super-hot plasma cooled, the transition to ordinary matter might have been patchy. Some regions of the cosmos could have frozen slightly earlier or later than others. Some pockets might have had a slightly different density or energy. These irregularities in the phase change could have had a profound consequence, tipping the delicate balance between protons and neutrons. Remember, the neutron-to-proton ratio is the master control for helium production. In a perfectly smooth transition, this ratio is set by the weak nuclear force and freezes in just before nucleosynthesis begins. But if the quark-gluon plasma froze unevenly, certain regions might have ended up with a small excess of neutrons. Imagine two adjacent patches of the early universe cooling from the plasma state. In one patch, the conditions during the freeze subtly favor the formation of neutrons over protons. When the nuclear furnaces of Big Bang Nucleosynthesis ignite a few minutes later, this neutron-rich pocket burns hotter and faster. It fuses a higher percentage of its hydrogen into helium, Meanwhile, a neighboring patch that froze with a more standard balance produces the expected 25% helium. The result is a cosmos that is not perfectly mixed. Instead of a uniform sea of hydrogen and helium, the universe's first atoms might have been arranged in a subtle, large-scale patchwork, with some regions slightly enriched in helium and others slightly depleted. This primordial unevenness would have been the very first structure, long before stars or galaxies. Over billions of years, gravity would have smoothed out these differences as matter clumped together, but a faint fossil of that initial patchwork might still linger in the oldest, most pristine gas clouds we can observe. This theory connects the most extreme physics of the first microsecond directly to the chemical makeup of the universe we see today. The recipe for the first elements was not just written during the 3 minutes of nucleosynthesis, but was potentially decided in that fleeting instant when quarks first decided to bind together for good. The quark-hadron transition was not a gentle cooling. It might have been a violent cosmic boiling. If this phase change was first order, akin to water erupting into steam, the early universe would have been a seething cauldron. In such a scenario, the shift from the free-roaming quark-gluon plasma to the confined world of protons and neutrons would not happen everywhere at once. Instead, tiny bubbles of the new phase would nucleate randomly in the superheated plasma, then rapidly expand and merge. Picture a pot of water just beginning to boil. You do not see the entire surface turn to steam instantly. Small bubbles of vapor form at the bottom, grow and rise, churning the liquid as they go. In the cosmic version, these bubbles were not of steam, but of the new hadronic phase, the state of matter where quarks are bound. As these bubbles expanded, they pushed the remaining quark-gluon plasma into shrinking, dense walls between them. This is where the magic, or rather the profound asymmetry, happens. Protons and neutrons, known collectively as baryons, are not created equally in both phases. Theoretical models suggest baryons would have a strong preference for the dense, quark-rich walls, the last remnants of the old plasma state. They would be swept up and concentrated there like dust gathered by a rolling snowball. When the transition finally completed and the last wall vanished, the universe would not have been a smooth blend. It would have been a chaotic, lumpy patchwork. Instead of a uniform sea of protons and neutrons, you would have vast regions of space that were almost empty, punctuated by incredibly dense knots and sheets of baryonic matter. These were not galaxies or stars. They were primordial overdensities on a scale we can barely conceive, where the density of nuclear fuel could be thousands of times higher than the cosmic average. This sets the stage for a radically different episode of Big Bang nucleosynthesis. In the standard model, the universe expands and cools so rapidly that nuclear reactions only have time to build elements as heavy as lithium. The denser pockets in an inhomogeneous model, however, change everything. Within those concentrated walls of protons and neutrons, the nuclear reactions would not just be faster, they would run along entirely different pathways. The sheer density means particles collide far more frequently. The chain that normally stops at helium-4 could keep going. 2 helium-4 nuclei or alpha particles could fuse into unstable beryllium-8, which normally decays in a tiny fraction of a second. But in these ultra-dense environments, that fleeting beryllium-8 nucleus might be struck by another alpha particle before it has a chance to fall apart, creating a stable carbon-12 nucleus. This is the famous triple alpha process, the same reaction that powers the hearts of red giant stars billions of years later. According to this theory, the very first carbon in the universe might not have been forged in the first generation of stars. It could have been cooked in the furious, fleeting instants following the quark-hadron transition, a product of the universe's own violent birth pangs. This is a staggering proposition. It suggests the raw ingredients for life, the carbon in our very bones, might have an origin far more ancient and exotic than we ever imagined. born not in stellar furnaces, but in the explosive freezing of space-time itself. The challenge for this theory is survival. Could these early, fragile carbon nuclei have endured the remaining heat of the Big Bang? Could they have been mixed back into the broader universe without being destroyed? The answers are uncertain, but the mere possibility reshapes our entire timeline of cosmic chemistry. Gravity is the universe's great architect, but in its most extreme form, it becomes something else entirely. Black holes are not merely cosmic vacuums, they are engines of unimaginable violence, warping space and time around them. Now, consider a theory that places these monsters in the nursery of creation itself. The primordial black hole catalysis theory suggests that among the first particles and photons, the universe may also have birthed a population of tiny, microscopic black holes. These would not be the stellar mass giants formed from collapsing stars, nor the supermassive behemoths at galactic centers. These would be quantum black holes, perhaps as small as an asteroid or even a mountain, forged from the intense density fluctuations in the first fraction of a second after the Big Bang. And their presence would have turned the calm soup of nucleosynthesis into a scene of gravitational chaos. Imagine a single, dense knot in the early plasma. Its immense gravity would act like a powerful magnet for the surrounding protons, neutrons, and light nuclei. As these particles spiraled in, they would be accelerated to incredible speeds, colliding with ferocious energy. In the diffuse plasma of the Standard Model, particles rely on random thermal motion to overcome their mutual electrical repulsion and fuse. It is a slow, statistical dance. But around a microscopic black hole, gravity takes over. It forces nuclei together, slamming them into one another at velocities far beyond what the ambient temperature alone could provide. This is not gentle fusion, it is gravitational hammering. This violent process could open up nuclear pathways that were otherwise closed. The standard 3-minute window only allows for reactions that proceed quickly. But with a black hole as a catalyst, even rare and slow reactions could become significant. For instance, the creation of elements slightly heavier than lithium, like beryllium or boron, which are notoriously difficult to make in stars, might have found a fleeting foothold here. More subtly, these black holes could have created stark local anomalies. A region of space hosting just one of these entities would have its nuclear fuel rapidly processed. The hydrogen and helium around it might be burned into different isotopes, or the delicate balance that produces lithium could be completely disrupted. The black hole would act like a voracious, radioactive chef, overcooking its immediate portion of the primordial soup while leaving the rest of the cosmic kitchen untouched. The aftermath is just as intriguing. What happened to these tiny black holes? Some may have evaporated via Hawking radiation, vanishing in a final burst of energy that could have further heated and mixed the local gas. Others, if they were just massive enough, could have survived to the present day, drifting through the galaxy as unseen, ancient relics. This theory transforms our view of the early universe from a smooth, expanding fireball into a landscape dotted with gravitational maelstroms, each one a frenzied forge where the rules of nuclear physics were bent by sheer gravity. The light elements we measure today would then be an average, a blend of the quiet cosmic background and the wild, energetic output of these first and most primal monsters. Supersymmetry is a grand vision of particle physics, a theory so elegant it feels like it must be true. It proposes that for every known particle in our universe, there exists a hidden superpartner. For every quark, there is a squark. For every electron, a selectron. For every photon, a photino. This symmetrical doubling of reality is not just mathematical beauty, it solves profound puzzles like the nature of the elusive dark matter that binds galaxies. The lightest of these superpartners is stable, neutral, and pervasive, a perfect candidate for the invisible cosmic scaffold. But in the furnace of the first moments, the story might have been different. The supersymmetric particle decay theory suggests that this lightest superpartner was not always stable. In the extreme heat, it could have briefly existed in an excited, heavier state before settling down. And its decay back to stability would have been a cosmic event. Picture a universe that has already cooled enough for the first protons and neutrons to form. The nuclear assembly line of Big Bang Nucleosynthesis is about to begin. Suddenly, throughout this infant cosmos, countless supersymmetric particles reach the end of their fleeting lives. They do not vanish quietly. Each one decays in a burst of energy, releasing a shower of high-energy photons, quarks, or even exotic particles back into the mix. This is not a gentle warming. It is a sudden, localized reheating of the cosmic soup. Think of a pot of water that has just stopped boiling. You turn off the burner and the surface begins to calm. Then someone drops in a handful of red-hot coals. Around each coal, the water violently bubbles and steams again, creating chaotic, boiling patches amid the general calm. The decay of these supersymmetric particles acts like those red-hot coals. It injects intense energy into specific regions, effectively restarting the clock on nuclear reactions in those patches. For a brief moment, the temperature in these zones surges back above the threshold for fusion. Protons and neutrons that had already begun to settle into a predictable pattern are suddenly thrown back into the frantic dance of creation and destruction. This secondary wave of nucleosynthesis would have a unique signature. The nuclear pathways that dominate depend on the exact conditions, and a sudden reheating event could favor different chains than the initial smooth cooling. The delicate balance that produces lithium-7 in the standard model is especially vulnerable. A burst of high-energy photons from the decays could blast apart the fragile beryllium-7 nuclei that are lithium's precursors, effectively destroying the element before it can fully form. This could naturally account for the observed lithium shortfall, but the implications run deeper than fixing one number. This theory offers a direct, testable link between the universe's first chemical elements and the most sought-after frontier in modern physics. We are not just talking about tweaking a parameter in an old model. We are talking about detecting the fossilized imprint of particles that may be produced at the Large Hadron Collider or discovered in deep underground detectors searching for dark matter. The recipe written in hydrogen and helium becomes a Rosetta Stone, translating the conditions of the first minutes into predictions for the particle zoo of tomorrow. The lightest elements are no longer just relics. They are messengers from a hidden, symmetrical layer of reality that flickered into existence and then vanished, leaving only its chemical signature behind. But what is the source of that asymmetry itself? The answer might lie not in particles, but in fields. The Erfolg-Dyn mechanism proposes a breathtakingly elegant origin story for all the matter in the universe. It begins with a special kind of cosmic field, a scalar field, similar to the one thought to have driven inflation, the universe's explosive initial growth. In the seething energy of the first moments, this field was not sitting still. It was oscillating, rolling through a complex landscape of potential energy like a marble on a warped tray. The precise path it took, the specific way it rolled and settled, is the key to everything. This rolling motion, according to the theory, can inherently violate the symmetry between matter and antimatter. As the field evolved, its oscillations could have imparted a net charge, a preference for matter over antimatter, directly into the fabric of the cosmos. This is not a minor adjustment. This process, called baryogenesis, is the moment the universe decided to be made of something rather than nothing. It generated the very first excess of protons and neutrons over their antimatter twins. And critically, this did not happen in some distant, disconnected epoch. The Erfolg-Dyn mechanism likely unfolded during or just before the window of Big Bang nucleosynthesis. The timing is everything. It means the process that filled the universe with permanent matter also set the precise conditions for cooking the first elements. Think of it as a cosmic kitchen where the chef not only prepares the meal, but also creates the very ingredients from empty space, all in one continuous flowing motion. The amount of matter generated, the baryon density, is the single most important number plugged into the equations of Big Bang Nucleosynthesis. It dictates the neutron to proton freeze out. It controls how efficiently hydrogen fuses into helium, and it predicts the exact trace amounts of deuterium and lithium. In this view, the 25% helium abundance is not a lucky coincidence. It is a direct signature of the baryogenesis event itself. The light elements are a fossilized record of the field's final role, its last oscillation before settling into the quiet state we see today. This creates a profound and testable link. By measuring the primordial abundances of hydrogen, helium, and deuterium with exquisite precision, we are not just testing nuclear physics. We are reverse engineering the behavior of a fundamental field in the first instance of time. A discrepancy in the predicted lithium yield, for instance, might not point to a problem with nucleosynthesis, but to a subtle detail in how that primordial field decayed and transferred its asymmetry into the particle soup. The universe's first recipe, then, is written in the language of quantum fields. Every atom in our bodies originated from the graceful, asymmetric dance of a scalar field in the newborn cosmos. Yet this elegant supersymmetric world introduces a dangerous character, the gravitino. If the photon has a photino and the electron a selectron, then the graviton, the hypothetical particle that carries the force of gravity, must have its own superpartner. This is the gravitino, and its theoretical existence creates a serious cosmological headache. The gravitino problem is a classic clash between beautiful particle theory and hard cosmic evidence. In the hot, dense early universe, gravitinos would have been produced in abundance, just like all other particles. Their fate, however, hinges on two terrifying possibilities, each one a threat to the universe we see. First, if the gravitino were light and stable, it would behave exactly like a massive, weakly interacting particle, a prime candidate for dark matter. That sounds good, but there is a catastrophic catch. Calculations show that the sheer number of gravitinos produced in the early cosmos would have given the universe far too much mass. Their collective gravity would have caused the cosmos to collapse back on itself in a fiery big crunch long before the first star ever twinkled. The fact that we are here in an old and expanding universe rules out this light, stable gravitino scenario. So the gravitino must decay, but the second possibility is just as destructive. If the gravitino were slightly heavier and decayed during or just after the epoch of Big Bang nucleosynthesis, it would have been a universe-wrecking event. A decaying gravitino would release a torrent of high-energy particles and radiation into the primordial soup. This sudden injection of energy would have violently reheated the cosmos, scrambling the delicate nuclear reactions in progress. It would be like throwing a lit firecracker into a chemist's carefully measured experiment. The predicted abundances of helium, deuterium, and lithium would be obliterated, leaving results that look nothing like the pristine patterns we actually observe in ancient gas clouds. The universe's successful recipe for the first elements places a tight constraint on this particle. The gravitino, if it exists, must have been either so incredibly heavy that it decayed almost instantly, vanishing well before nucleosynthesis began, or the conditions after inflation must have been such that gravitinos were never produced in large numbers to begin with. This leads physicists to a fascinating solution, a low reheating temperature. After the inflationary period blew up the universe to macroscopic size, it had to reheat, filling itself with the hot particle soup of the Big Bang. If that reheating temperature was kept relatively low, below about 10 trillion degrees, the production of gravitinos would have been suppressed. They would have been rare guests at the cosmic party, and their decay, whenever it happened, would have been too insignificant to disturb the cooking of the first elements. Alternatively, the gravitino itself could have been extraordinarily massive, causing it to decay almost immediately after birth, leaving no trace during the critical 3-minute window. This is not just a clever fix, it is a powerful example of how the fossil record of Big Bang nucleosynthesis acts as a strict referee for particle physics. A theory can be mathematically beautiful, but if it predicts a gravitino that disrupts the observed helium abundance, that theory must be adjusted or abandoned. The light elements become a cosmic litmus test, their unchanging ratios a guardrail that guides us toward a viable history of the universe, one where the hidden particles of supersymmetry, if they are real, had the decency to stay out of the kitchen during the most important bake-off in history. The very fabric of space-time might have more dimensions than we can perceive. This is the core of brain-world cosmology, a vision inspired by string theory where our entire 4-dimensional universe is not all there is. Instead, it is a membrane or brain floating within a higher dimensional expanse called the bulk. In this model, all the forces and particles we know, like electromagnetism and the nuclear forces, are trapped on our brain. They cannot escape into the higher dimensions. Gravity, however, is different. It is the curvature of space-time itself, and in these models, it can leak off our brain and seep into the bulk. This leakage has a profound and testable consequence for the universe's first 3 minutes. It changes how gravity behaves on the largest scales, which in turn changes how fast the universe expanded during Big Bang nucleosynthesis. In the standard model, the expansion rate is governed by the density of radiation and the strength of gravity as described by Einstein's equations. But if gravity was leaking away, its effective strength in our universe would be weaker during that epoch. A weaker gravity would mean the universe expanded more slowly because the pull holding it back was diminished. Conversely, in some brain world scenarios, effects from the bulk could make gravity appear stronger, causing a faster expansion. This single change, a modified expansion rate, is like changing the timer on the cosmic oven. The entire nucleosynthesis process is exquisitely sensitive to how quickly the universe cools. A faster expansion means the temperature drops below the fusion threshold sooner, cutting the nuclear reactions short. With less time, fewer neutrons get captured into helium nuclei. The predicted abundance of helium-4 would drop significantly below the standard 25%. Deuterium, however, which is easily destroyed in stars, would be overproduced because the reactions that would normally burn it into helium did not have time to complete. A slower expansion has the opposite effect. The universe stays hot and dense for longer, giving the nuclear chain reactions more time to run to completion. Nearly every available neutron gets used up, producing a helium abundance much higher than 25%, and leaving almost no deuterium behind at all. Our actual, observed universe sits perfectly between these two extremes. The measured abundances of helium and deuterium match the standard model's prediction with astonishing precision, implying the expansion rate during those first minutes was exactly as Einstein's gravity predicts. This places a powerful constraint on brain-world models. They are not ruled out, but they must be crafted so that any leakage of gravity into the bulk was negligible during the nucleosynthesis era. The first light elements, therefore, act as a cosmic probe for extra dimensions. They tell us that if our universe is a membrane in a higher dimensional bulk, then during its first few minutes, it must have been a very sticky membrane indeed, one that held onto gravity with a tenacious grip. The recipe for hydrogen and helium becomes a test of the universe's very architecture, confirming that the gravity which shaped the first atoms behaved exactly as if it were confined to the familiar 4 dimensions of our reality. Einstein's theory of gravity is a masterpiece, but is it the final word? Scalar tensor gravity theories propose a fascinating twist. In these models, the strength of gravity is not a fixed constant. Instead, it is mediated by a dynamic cosmic field, a scalar field that can change over time and space. This field acts like a universal dimmer switch for gravity itself. In the calm of today's universe, the switch is set to a specific position, giving us the gravity we measure and feel. But rewind to the furnace of the first minutes, and the story could be dramatically different. In that extreme environment, the scalar field might have been in a wildly different state, perhaps oscillating or settling into its minimum. If the field's value was higher or lower back then, the effective strength of gravity would have been different. This directly changes a single critical number in the cosmic equations, the Hubble expansion rate, h. This rate is the speedometer of the universe's expansion. In the standard Big Bang Nucleosynthesis model, h has a very specific value dictated by the density of radiation and Einstein's gravity. Change the strength of gravity and you change h. A stronger effective gravity in the early universe would mean a faster expansion rate. The universe would have cooled more rapidly, cutting the nuclear cooking time short. The consequences for the light elements are precise and severe. With less time, fewer neutrons would be captured into helium nuclei. The predicted helium-4 abundance would drop. Conversely, deuterium, which is destroyed as the reactions proceed, would be overproduced because the chain that burns it would be interrupted. The opposite is also true. A weaker gravity and a slower expansion would give the reactions more time, burning nearly all the deuterium and producing an overabundance of helium. Our universe, as we measure it, sits perfectly on a knife's edge between these two extremes. The observed abundances of helium-4 and deuterium match the standard model's predictions with a precision of better than 1%. This is not a rough agreement, it is a Loctite constraint. It tells us that during those first 3 minutes, the effective strength of gravity must have been almost exactly what Einstein's theory predicts. Scalar tensor theories are not ruled out, but they are forced into a corner. To survive, they must be designed so that the scalar field was effectively frozen, or pinned to a value that mimics Einstein's gravity, precisely during the nucleosynthesis window. Any significant deviation would have left an unmistakable chemical fingerprint in the oldest stars, a fingerprint we simply do not see. Therefore, the primordial abundances of hydrogen and helium become one of the most sensitive probes we have for testing the very fabric of gravity. They are a cosmic experiment conducted in the first moments, whose results are written across the sky. The recipe for the first elements confirms that, for all its potential complexity, gravity behaved with a stunning simplicity when it mattered most, crafting a universe stable enough for us to one day ask why. Alpha is a number so fundamental it feels like a law of the universe. The fine structure constant, approximately 1 over 137, dictates the strength of the electromagnetic force. It controls how tightly electrons bind to atoms, how light interacts with matter, and crucially for our story, how strongly atomic nuclei repel each other. For decades, this number was considered immutable, a true constant woven into the fabric of reality. Then came the quasars. By analyzing the ancient light from these brilliant beacons as it passed through billion-year-old gas clouds, astronomers noticed something unsettling. The absorption lines in the spectra, the fingerprints of distant atoms, appeared slightly shifted in a way that suggested the fine structure constant, alpha, was minutely smaller in the early universe. The change is almost unimaginably tiny, perhaps just a few parts in a million over billions of years, but its implications for the first moments are seismic. If alpha was weaker in the past, then the electromagnetic force was weaker. This changes everything about the cosmic kitchen. The primary barrier to building elements in the first 3 minutes is the positive charge of atomic nuclei. Two protons fiercely repel each other because of their identical charge. To fuse, they must collide with enough energy to overcome this electromagnetic barrier, a hurdle set by the strength of alpha. In the standard model, with today's alpha, that hurdle has a specific height, but if alpha was slightly smaller back then, the hurdle was lower. Protons and other nuclei would have repelled each other less fiercely. At first glance, this sounds like it should make fusion easier. With a lower barrier, particles could fuse more readily, potentially creating more helium. But nuclear physics is never that simple. A weaker alpha also means the nuclear force, which binds protons and neutrons together, operates in a slightly altered landscape. The delicate balance between the repulsive electromagnetic force and the attractive strong nuclear force inside a nucleus shifts. This can affect the stability of the isotopes involved in the nucleosynthesis chain. Most significantly, it changes the rates of every single nuclear reaction. Calculations show that a smaller alpha in the past would have made certain key reactions, like the formation of deuterium from a proton and a neutron, proceed less efficiently. It is a subtle throttling of the entire process. Think of trying to assemble a delicate puzzle with magnets. If you slightly weaken the magnets, the pieces do not snap together as decisively. They might hesitate or fail to connect at the precise moment needed. In the rapidly cooling early universe, timing is everything. A small reduction in reaction efficiency means the whole cascade from hydrogen to helium stutters. With less time before the universe becomes too cool, the final yield of helium-4 could be reduced. This offers a potential pathway to addressing subtle tensions in the data. While the observed helium abundance is very close to 25%, some of the most precise measurements from extremely pristine regions show a value that is marginally, tantalizingly lower. A varying alpha could naturally account for that whisper of a discrepancy. It would also recalibrate the predicted amounts of deuterium and lithium, potentially bringing theory into even closer alignment with observation. The quest to confirm this variation is ongoing, with different teams analyzing quasar light and reaching different conclusions. Yet the mere possibility forces us to confront a staggering idea. The laws of physics, as expressed in their fundamental constants, might not be fixed monuments. They could be more like cosmic dials slowly turning over eons. If alpha was indeed different during Big Bang nucleosynthesis, then the first elements are not just a product of physics. They are a fossilized record of physics itself evolving, a chemical signature of a time when the universe's own rules were still settling into the form we know today. Neutrinos are ghostly, but in the first seconds they held real power over the cosmos. While photons of light provided the dominant pressure in most of the universe, there is a compelling possibility that this was not the case everywhere. The 16th theory explores a radical departure from the standard smooth soup, proposing the existence of primordial neutrino-dominated regions. In these pockets of space, the density of ghostly neutrinos was so immense that they, not photons, dictated how that local patch of the universe expanded and cooled. This creates a dramatically different kitchen for cooking the first elements. Photons are relentless destroyers in the early universe. Their high energy blasts constantly ripping apart fragile deuterium nuclei. But in a region dominated by neutrinos, the pressure and expansion dynamics shift. Neutrinos interact with matter even more weakly than photons, meaning they decouple from the cosmic soup earlier and exert a smoother, less disruptive pressure. In such a zone, the universal expansion might have proceeded at a slightly different pace. Crucially, the photon bath, the main threat to deuterium, could have been comparatively weaker locally. This means the deuterium bottleneck, that critical moment when deuterium becomes stable, could have broken earlier there. With deuterium surviving more readily, the entire nuclear chain reaction kicks off sooner. The assembly line for helium has more time to run before the universe cools too much. One possible outcome is that these neutrino-dominated pockets became tiny helium factories, producing a higher local abundance of helium-4 than the cosmic average. But the effects could be even more specific. The precise pathway to lithium-7 is a delicate ballet of temperatures and densities. A neutrino-dominated environment with its altered expansion history might have provided the perfect conditions for that ballet to proceed more efficiently. While the rest of the universe struggled to make much lithium, these special zones could have been lithium nurseries, synthesizing more of the elusive element. The result, once everything mixed together over billions of years, would be a subtle patchwork quilt of elemental abundances imprinted on the cosmos. We would not see distinct borders today, but the average we measure from ancient gas clouds would be a blend of these different primordial kitchens. The observed lithium shortfall, then, might not be a universal failure of the standard model. It could be an averaging artifact. If lithium was overproduced in some neutrino-dominated regions but underproduced elsewhere, the final mix we detect could still fall short of the prediction for a perfectly uniform universe. This theory forces us to envision an infant cosmos of stunning complexity, not a single simmering pot but a collection of distinct cauldrons, each simmering under the influence of a different dominant force. The light elements become a blended record, a fossilized whisper of a time when ghostly neutrinos ruled entire domains of reality. Dark energy is the mysterious force accelerating the universe's expansion today, but what if it was not a late arrival? A dynamic form of dark energy might have been present from the very beginning, a phantom guest in the primordial kitchen. This early dark energy would have contributed to the total energy density of the infant cosmos, acting like an extra source of outward pressure. In those first few minutes when radiation ruled, even a small additional component would have had an outsized effect. More energy density means a stronger push against gravity's pull. The universe would have expanded faster, cooling at an accelerated rate. For Big Bang Nucleosynthesis, this change is the most critical variable of all time. The entire process is a frantic race against the cooling clock. Speed up the expansion and you effectively shorten the race. The window for nuclear fusion slams shut sooner. With less time available, the chain reactions that build helium-4 from hydrogen cannot run to completion. Fewer neutrons get captured into stable helium nuclei before the temperature plummets below the fusion threshold. The predicted yield of helium-4 would be reduced. This is not a catastrophic change, but a subtle, precise shift. In the standard model, helium makes up about 25% of the ordinary matter by mass. Early dark energy could nudge that number downward, perhaps to 24.5 or even 24%. Intriguingly, some of the most careful observations of pristine gas in the oldest corners of the cosmos hint at a helium abundance that is marginally lower than the textbook prediction. It is a whisper of a discrepancy, but in the precise science of cosmology, whispers are shouts waiting to be understood. Early dark energy offers a compelling narrative to explain that whisper. It suggests the force that now drives galaxies apart was also there at the dawn, subtly stirring the pot and leaving its fingerprint in the very first element forged. This idea connects two cosmic epochs separated by billions of years. The same mysterious essence shaping the universe's fate today may have also written the first line in its chemical history. The laws of physics are written in fields, but their relationship with gravity is not always simple. Some of the most profound theories suggest that the scalar field responsible for the universe's explosive inflation was not a passive tenant in spacetime. It was actively shaping the gravitational landscape through a non-minimal coupling. This means the field's energy and gravity were intertwined, each directly influencing the other's behavior. In models like Higgs inflation, the very same field that gives particles their mass in today's universe may have once driven its exponential growth. This deep connection changes a fundamental equation: how the energy stored in that primordial field faded away as the cosmos expanded. After inflation ended, that colossal energy had to go somewhere. It reheated the universe, dumping its contents into the hot particle soup of the Big Bang. The rate at which this happened, the precise temperature-time relationship as the field decayed, is the hidden timer for everything that followed, including Big Bang nucleosynthesis. If the field was minimally coupled, its energy dilutes in a predictable way as space stretches, like ink diffusing evenly in calm water. But a non-minimal coupling twists this process. The interaction with gravity can make the field's energy dissipate faster or slower, effectively changing how quickly the universe transitions from the cold emptiness after inflation to the seething heat required for nuclear fusion. This alters the initial conditions for the cosmic kitchen. A faster transfer of energy might lead to a slightly hotter starting point for nucleosynthesis, or a different distribution between radiation and other particles. Even a tiny shift here propagates through every calculation. It can affect the exact moment protons and neutrons freeze out, the precise density of baryons, and the final yields of helium and deuterium. Therefore, the pristine abundances of these light elements become a powerful testbed for the physics of inflation itself. We cannot see the inflationary field directly, but we can read the recipe it left behind in the first atoms. A successful model of inflation must not only create a smooth, flat universe, it must also reheat it in such a way that the resulting nuclear alchemy matches the heavens we observe. The helium in every star is a cosmic signature, waiting to confirm or challenge our boldest ideas about the universe's first trillionth of a second. Mirror matter is not science fiction, but a serious theoretical possibility. This theory suggests our universe has a hidden twin, a perfect copy of particles and forces that exists alongside our own. In this mirror world, there could be mirror protons, mirror neutrons, and mirror electrons, all obeying the same physical laws but completely invisible to us. The only bridge between our world and the mirror world is the weakest force of all, gravity. For all other interactions, the two realms are perfect strangers, unable to see, touch, or communicate. Yet during the universe's first 3 minutes, this ghostly twin would have been cooking its own meal. While our sector was busy fusing hydrogen into helium, the mirror sector was undergoing its own identical process of Big Bang Nucleosynthesis. They would have started with the same ingredients and the same recipe, running in perfect parallel. But here is where things get interesting. Even though the two sectors do not directly interact, they are linked by the shared fabric of space-time. They expand together, they cool together, and crucially, they can exchange energy through gravitational interactions. Think of two separate kitchens inside the same house, each baking their own cake. The kitchens are sealed off from each other, but they share the same heating and cooling system. If one oven is running hotter, it can subtly warm the air in the walls, which then transfers a tiny amount of heat to the other kitchen, changing its ambient temperature. In the cosmic version, the mirror sector could have had a slightly different temperature than our own, perhaps because of a minute asymmetry in how the two worlds were born. As both sectors expanded, energy could have slowly leaked from the hotter one to the cooler one through their gravitational connection. If our sector was the one receiving this extra energy, even a minuscule amount, it would have changed everything. The temperature of our primordial soup would have been ever so slightly higher during those critical minutes. A higher temperature means particles are moving faster and colliding more frequently. Nuclear reaction rates are incredibly sensitive to temperature, changing by orders of magnitude with just a small tweak. This gravitational heating from the mirror world could have accelerated the fusion reactions in our sector. The assembly line for helium would have run a little faster, potentially capturing a few more neutrons and producing a slightly higher final abundance. More subtly, it could have altered the delicate timing that governs the creation of lithium, either enhancing or suppressing its production in ways that might explain the observed shortfall. The beauty of this theory is its testability. It makes a specific prediction. Since the mirror sector would have formed its own light elements, it would also have its own cosmic microwave background, a mirror afterglow from its own hot, dense beginning. The gravitational influence of all that mirror matter and radiation could leave faint, distinctive patterns in the large-scale structure of our visible universe, or in the precise way galaxies cluster together. Astronomers are already searching for these ghostly gravitational footprints. The mirror matter theory transforms our view of the first elements from a solo performance into a cosmic duet. The recipe we see imprinted in hydrogen and helium may not be ours alone. It could be a blended record, a harmony sung between two separate worlds that have never directly met, their only connection the silent, pervasive pull of gravity that shaped them both. But this line of thinking leads to a profound, almost philosophical question. Why do the constants of nature have the exact values that allowed for this precise, life-permitting recipe? One answer ventures beyond physics into the realm of cosmic destiny, the anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers like us. We are here to measure the helium abundance, therefore the universe had to produce a helium abundance that allowed for our emergence. This is not a scientific explanation in the traditional sense, but a logical filter. Apply this filter to Big Bang nucleosynthesis, and the numbers take on a new, startling significance. The 25% helium figure is not just a random outcome of nuclear physics. It may be a cosmic prerequisite. Think about what happens if you tweak that number. If the early universe had produced a significantly higher abundance of helium, say 40 or 50%, the consequences for cosmic evolution would be catastrophic. Stars which are fueled by fusing hydrogen into helium would have started their lives with a much smaller reservoir of hydrogen fuel. They would burn hotter, brighter, and exhaust themselves in a cosmic blink. The universe would be filled with short-lived, violent stars, leaving no time for stable planetary systems to form, let alone for the slow, patient chemistry of life to begin. Conversely, what if the helium yield were much lower, perhaps only 10%? In that scenario, the early universe would have been almost pure hydrogen. While stars would have plenty of fuel, the lack of heavier initial elements could drastically alter how the first structures collapsed. Helium plays a subtle but important role in how gas cools and condenses to form galaxies. A severe shortage might have prevented the efficient formation of the very galaxies that become stellar nurseries. We might have ended up with a dark, diffuse cosmos where matter never quite gathered itself into the brilliant islands we call home. The anthropic principle suggests our observed light element abundances sit in a remarkably narrow Goldilocks zone. Not too much helium, not too little, but just right for a long-lived, structured universe capable of forging carbon, oxygen, and eventually curious minds. This perspective does not tell us how the constants were set to these life-allowing values. That remains the domain of physics, but it reframes the meaning of the data. The successful predictions of Big Bang nucleosynthesis are more than a triumph of calculation. They are a signature of a universe that, from its very first minutes, was already tuned with the potential for complexity. The recipe written in hydrogen and helium is not merely a relic of the past. It is the first page of a story that had to be written precisely this way for any of us to be here to read it. The universe's first recipe might have been written before time itself began. Our journey through the theories of the first light elements now leads us to the ultimate frontier of speculation, a moment before the Big Bang. String gas cosmology offers a breathtaking vision of this pre-beginning. It proposes that the fundamental ingredients of reality are not point-like particles, but tiny, vibrating loops of energy called strings. In this view, the universe did not erupt from a singular point of infinite density. Instead, it emerged from a hot, dense, and chaotic tangle of these strings, a primordial state of maximum disorder where all directions and dimensions were equivalent. This was not an explosion, but a gradual unwinding from a state of thermodynamic equilibrium, a cosmic, not slowly coming loose. The behavior of this stringy gas, its thermodynamics and vibrations, would have dictated everything that came next. As this tangled phase began to expand and cool, the vibrations of the strings settled into specific patterns. Think of a vast orchestra tuning before a symphony. In the chaotic noise, every instrument is sounding at once, but as the conductor raises the baton, the noise resolves into distinct notes. In string gas cosmology, the act of expansion is the conductor. The specific vibrational patterns that became stable as the universe grew determined the identities and properties of the first particles. A string vibrating one way became a quark. A string vibrating another way became an electron. The density of each particle species, the very number of protons versus neutrons available for nucleosynthesis, was not a random initial condition. It was a direct output, a thermodynamic relic of this stringy prehistory. This means the initial conditions for Big Bang nucleosynthesis, the precise baryon density and the neutron-to-proton ratio, were not simply plugged in at the start of the equations. They were computed by the physics of the string gas phase. The universe's expansion smoothed out the tangles, and the vibrating strings froze into the familiar particles of the Standard Model, which then immediately began the nuclear reactions we have been exploring. The helium abundance we measure today, therefore, could be a direct echo of the vibrational modes of strings in that primordial hot gas. This theory completely reframes the origin story. The first 3 minutes are not the opening act but the second chapter. The real genesis occurred in a realm before conventional space and time, where the rules were written by the thermodynamics of fundamental strings. The light elements become a cosmic fossil from a pre-geometric era, a chemical message encoded by the universe's very first vibrations. Collisions on a cosmic scale could rewrite the entire origin story. The ekpyrotic or cyclic universe model offers a vision where the Big Bang is not the beginning of time, but a violent, recurring event in an eternal cosmic rhythm. In this breathtaking framework, our entire four-dimensional universe exists on a membrane or brain, floating in a higher dimensional space. Parallel to us drifts another brain, a hidden, separate reality. The two are drawn together by an invisible force, moving on a slow, inevitable collision course over trillions of years. When they finally meet, the impact is cataclysmic. It releases an unimaginable firestorm of energy and matter, igniting what we perceive as our Big Bang. The universe expands, cools, and evolves for eons, just as we observe. But this is not the end. After all its energy is spent and expansion grinds to a halt, the gravitational pull between the brains draws them together once more. The cycle repeats eternally. In this view, our cosmos has no true beginning and no final end, only an endless sequence of births from collision. This radically changes the meaning of Big Bang nucleosynthesis. It was not a singular, unique event at time zero. It was the most recent in an infinite series of cosmic dawns. Each collision, each new bang, creates a fresh, hot, dense state from which light elements can be forged anew. But does each cycle produce the same recipe? The answer depends on what survives the Great Crunch. In some versions of the model, the collisions are so perfectly symmetric that they reset the cosmic clock with near-identical conditions each time. The brains approach, collide, and rebound with a regularity that ensures the same density of protons and neutrons, the same expansion rate, and therefore the same 25% helium yield in every cycle. Our observed abundances are not a one-time miracle, but the inevitable, repeating output of an eternal machine. Other versions introduce a critical twist: entropy. Each cycle of expansion sees stars burn out, black holes evaporate, and disorder increase. This entropy does not vanish when the universe contracts toward the next collision. Instead, it is woven into the fabric of the brains themselves. When they collide and rebound to begin a new expansion, they do so with a slightly higher level of background entropy than the cycle before. This subtle change could alter the initial conditions for nucleosynthesis in the next universe. Think of a baker reusing a bowl without washing it perfectly. A tiny residue of the previous batter remains, subtly influencing the flavor and texture of the next cake. over countless cycles, these minute changes could accumulate. The baryon density, the balance of matter and radiation, or even the effective strength of the forces might drift. The helium abundance we measure today, then, would not be a fundamental constant of physics. It would be a local variable, a single data point in an endless sequence, reflecting the specific accumulated history of our particular cycle. This model challenges the very foundation of cosmology. It suggests that the pristine light elements we study are not clues to an absolute beginning, but pages from one chapter in an infinite book. The search for a unique, first-cause explanation for their abundances may be looking for a story that does not exist. Instead, we might be witnessing the most recent iteration of a process older than time itself, a recipe that has been cooked, served, and cleared away an infinite number of times before. But inflation itself might not have been a cold, empty affair. Standard models describe it as a supercooled expansion, where the universe stretches exponentially while the energy driving that expansion remains locked in a field, leaving the cosmos a vast, frigid void. Only when inflation ends does that energy finally convert into the hot particle soup of the Big Bang in a violent process called reheating. The warm inflation scenario paints a radically different picture. Here, the inflattened field does not hoard its energy. As it drives the fantastic expansion, it continuously and gently dissipates that energy into radiation, like a motor that runs hot. The universe never becomes a complete vacuum. Instead, it maintains a thermal bath throughout its incredible growth spurt. There is no sharp, catastrophic end to inflation followed by a sudden reheating. The transition from the inflationary epoch to the hot Big Bang is smooth, seamless, and warm. This continuous thermal history rewrites the prologue to Big Bang nucleosynthesis. In the standard story, the violent reheating phase can produce a zoo of exotic, heavy particles as the field decays. These relics, if they survive, become dangerous contaminants in the primordial soup, potentially decaying later and wrecking the delicate nuclear balances we have discussed. Warm inflation offers a cleaner start. Because the universe is always thermally populated, the production of these troublesome relic particles is suppressed. The energy transfer is too gentle to kick them into existence in large numbers. The cosmos that enters the nucleosynthesis era is a more purified, predictable place. This could have a direct effect on the light element yields. For instance, one of the gravest threats to the standard recipe is the late decay of massive particles, which can dump extra energy and neutrons into the mix, altering helium and lithium abundances. A warm inflation universe would have far fewer of these problematic relics from the start. The initial conditions for the nuclear chain reactions are not just set by the expansion, but by this gentler thermal prehistory. It is the difference between trying to bake a delicate soufflé in a kitchen that just experienced a boiler explosion versus one that has been maintained at a perfectly steady, warm temperature. The predictions for hydrogen and helium might become even more precise and robust, removing some of the theoretical uncertainties that other theories try to exploit. The appeal of warm inflation is its elegance. It unifies two cosmic epochs, inflation and the hot Big Bang, into a single, continuous narrative. The first light elements then become a test of this smoothness. If their observed abundances are ever found to be incompatible with the messy aftermath of a cold reheating, but perfectly aligned with the predictions of a warm, gentle transition, it would be a powerful clue. It would suggest that from its very first moments, the universe was not a place of jarring phase changes, but of a graceful, warm unfolding. Magnetic fields possess a hidden geometry, a twist in their very structure known as helicity. This is not just the direction of the field lines, but a measure of their knot-like linkage and corkscrew twist, a fundamental property that makes them more durable, like a tightly wound spring that resists unraveling. Some theories suggest the universe's first magnetic fields were born with this property, a net primordial helicity woven into the fabric of space-time. This subtle twist could have been a silent choreographer during the first 3 minutes, guiding the dance of charged particles in a profound and asymmetric way. In the seething plasma of Big Bang Nucleosynthesis, protons and electrons are not passive ingredients. They are charged and they spiral along magnetic field lines. A field with a dominant handedness, a preferred twist, would impart a preferential direction to this spiraling motion. Imagine a vast cosmic corkscrew. Particles would tend to follow its thread in one direction more easily than the other. This could create a chiral asymmetry in the plasma, an environment where left-handed and right-handed motions are not equally favored. And here is where physics connects the large to the unimaginably small. The weak nuclear force, which governs the vital conversions between protons and neutrons, is itself inherently chiral. It treats left-handed particles and right-handed particles differently. In our everyday world, this subtle bias is hidden, but in a primordial plasma churning under the influence of a helical magnetic field, that bias could have been amplified. The field's twist might have subtly favored the weak interactions of particles with one specific handedness. This could have altered the critical rates at which protons turned into neutrons and vice versa during those fleeting seconds before nucleosynthesis began. The neutron-to-proton ratio, the master control for all helium production, is set by a delicate balance of these weak interactions as the universe cools. A helical magnetic field, by tweaking the rates for left-handed versus right-handed particles, could have shifted that balance. It might have left the universe with a few more neutrons or a few less just before the nuclear furnaces ignited. That tiny shift would then ripple through every calculation, changing the final yields of helium, deuterium, and lithium in a unique fingerprint-like pattern. The helicity of the first magnetic fields, therefore, is not an abstract curiosity. It is a potential tuning dial for the cosmos, a geometric twist imprinted at birth that may have literally twisted the pathway of nuclear history, leaving its signature in the oldest atoms we can find. Neutrinos are shape-shifters of the cosmos. Today, these ghostly particles drift through space in 3 distinct flavors: electron, muon, and tau, constantly oscillating from one identity to another as they travel. But in the ultra-dense plasma of the first second, this quantum ballet was not a solo performance. It was a crowded, chaotic collective dance where every neutrino was constantly bumping into its own kind. This phenomenon, known as neutrino self-interactions, could have orchestrated a symphony of flavor changes with profound consequences for the first atoms. In that seething soup, neutrinos were not just passive spectators, they were a dominant component, outnumbering even protons and photons. Their constant collisions with each other created a tangled feedback loop. The flavor of one neutrino could influence the flavor of its neighbor, which in turn influenced another, leading to large-scale, synchronized oscillations that swept through the entire population. Think of a vast stadium wave where the rise and fall of each section is triggered by the movement of the crowd itself, not by any external signal. This collective behavior did more than just swap labels. It fundamentally changed how energy was partitioned among the neutrino flavors. In the standard model, we assume all 3 types had roughly the same energy distribution as they decoupled from the cosmic soup. But if collective oscillations redistributed that energy, shifting more of it into, say, electron neutrinos, the entire thermal balance of the weak freeze-out would be altered. This moment, the weak freeze-out, is the single most important event before nucleosynthesis begins. It is the instant the universe cools enough that the weak nuclear force can no longer keep protons and neutrons in equilibrium through constant conversion. The ratio of neutrons to protons is locked in, becoming the primary fuel for helium production. The temperature at which this freeze-out occurs is exquisitely sensitive to the energy density and behavior of neutrinos, especially electron neutrinos, because they participate directly in the conversion reactions. If collective oscillations made the electron neutrino population slightly hotter or more energetic, the weak interactions would have remained effective for a fraction of a second longer. This extra time would have allowed more neutrons to decay into protons or be converted, tweaking the final neutron-to-proton ratio downward. Even a change of less than 1% in this ratio would cascade through the subsequent nuclear reactions, altering the predicted helium yield by a measurable amount. The universe's recipe, written in that first second, may have been stirred not by a spoon, but by the ghostly, synchronized sway of a trillion neutrinos deciding together who they wanted to be. Among the universe's most elusive hypothetical guests is the action. Born from a brilliant solution to a deep puzzle in quantum chromodynamics, the theory of the strong nuclear force, actions are particles of profound subtlety. They are predicted to be incredibly light, fantastically weakly interacting, and they are a leading candidate for the mysterious dark matter that fills our cosmos. But in the fierce dawn of time, certain action models suggest they could have played a more dramatic, destructive role. Some actions are not perfectly stable. Over time, they can decay, vanishing into pairs of photons. The timing of this decay is everything. If a population of these actions decayed during or shortly after the epoch of Big Bang Nucleosynthesis, they would have flooded the universe with a soft glow of low-energy photons. This would not be a cataclysmic burst, but a gentle, persistent drizzle of light raining down on the newly formed atomic nuclei. To understand the consequence, we must look at the cosmic microwave background, the ancient afterglow of the Big Bang. This radiation has an almost perfect blackbody spectrum, a smooth curve of energy that tells us the early universe was remarkably uniform. An injection of extra photons from action decays would have subtly warped that perfect curve, creating what cosmologists call a spectral distortion, a tiny kink or bump in the energy distribution. But those extra photons would have done more than just distort an ancient light signature. They would have interacted with the fragile nuclei just freshly minted in the first 3 minutes. Deuterium, that heavy hydrogen nucleus, is particularly vulnerable. Its binding energy is low, a delicate thread holding it together. A shower of low-energy photons, even gentle ones, could have had just enough energy to snap that thread. This process is called photodisintegration. Imagine a child's tower of blocks carefully stacked. Now imagine a soft, steady breeze. It does not knock the tower over in one blow, but it can gradually loosen the top blocks until they tumble. The action's photon drizzle could have acted like that breeze, blasting apart a portion of the universe's newly formed deuterium, breaking it back down into solitary protons and neutrons. This loss of deuterium would have cascaded through the rest of the nuclear chain. Deuterium is the crucial stepping stone to helium. Less deuterium means the assembly line for helium-4 stutters. The final abundance of helium could be slightly reduced. More intriguingly, the destruction would not be uniform. It would depend on the exact timing and energy of the action decay. This offers a potential pathway to explain not just the lithium problem, but also subtle tensions in the measured deuterium abundance from different ancient gas clouds. The universe's recipe book in this theory bears an erasure mark, a page where some of the first entries, the deuterium nuclei, were partially scratched out by the fading light of dying actions. The search for this effect is a hunt on two fronts. In deep underground laboratories, physicists are trying to catch a whisper of actions from the dark matter halo of our galaxy. Meanwhile, high above the Earth, satellites like the proposed Pixie mission are designed to measure the cosmic microwave background with such exquisite precision that they could detect the spectral distortions left by that primordial photon drizzle. The first elements, therefore, might hold a clue to a particle we have never seen, a faint chemical signature written by a ghost that decayed into light, forever altering the balance of the infant cosmos. The quark-hadron transition was not a gentle, uniform freeze. It could have been a cosmic supercooling event, a violent snap from one state of reality to another. Picture a pond on a perfectly still, cold night. The water can sometimes remain liquid well below its normal freezing point in a precarious, supercooled state. Then a single disturbance, a leaf falling, a pebble dropping, triggers an instantaneous chain reaction. Ice crystals explode outward in a frantic, jagged pattern, freezing the entire surface in seconds. The early universe may have experienced a similar catastrophic phase change. As it expanded and cooled past the critical temperature for quarks to bind, nothing happened at first. The quark-gluon plasma remained in a supercooled, metastable state, a liquid refusing to freeze. Then, somewhere in that vast, seething ocean, a microscopic bubble of the new hadronic phase nucleated. This was not a calm process. The formation of that bubble released latent heat, creating a pressure wave that raced outward at nearly the speed of light. This shock front triggered the conversion of the surrounding supercooled plasma, which in turn released more heat and triggered more conversions. The universe did not freeze smoothly. It froze in a chaotic, explosive cascade of expanding bubbles and colliding shock waves. Turbulence ripped through the primordial soup on a scale we can barely fathom. This was not a kitchen, but a cosmic blender set to its highest setting. In this frenzy, the distribution of baryons, the protons and neutrons, was not decided by a calm statistical average. It was scrambled by the violence. Regions of slightly higher quark density were caught in the turbulent eddies and mixed with regions of lower density. Dense knots of nuclear fuel were shredded and strewn across the cosmos, while empty voids were injected with sudden bursts of particles from a collapsing shock front. The result was a primordial element map written not by predictable physics alone, but by chaos. The initial conditions for Big Bang nucleosynthesis in any given patch of space became stochastic, touched by randomness. One region, by sheer chance, might have been a dense pocket swept up by a passing shock wave. There, nuclear reactions would have run hot and fast, producing a local overabundance of helium. Another region, just a short distance away, might have been rarefied by an expanding bubble wall, leaving it fuel poor and helium deficient. The universe we see today, with its remarkably uniform elemental abundances, is the product of eons of mixing and averaging. But the oldest, most pristine gas clouds might still carry faint chemical fossils of that initial turbulence. Their exact ratios of deuterium to helium or lithium to hydrogen might not be identical. They could show subtle, random variations, a cosmic fingerprint of the violent and non-equilibrium birth of matter itself. This theory suggests the recipe for the first elements was not merely calculated, it was churned by the universe's own violent transition into existence. The universe's phase transitions may have left behind more than just a changed state of matter. They could have etched permanent scars into the fabric of space-time itself. These scars are known as topological defects, and they come in several terrifying forms. Cosmic strings are hypothetical one-dimensional cracks in reality, thinner than a proton but with the mass of a mountain range per inch stretching across the cosmos. Domain walls are two-dimensional sheets of concentrated energy, separating regions of space where fundamental fields settled into different values. These are not objects in the conventional sense. They are flaws in the cosmic crystal, immortal relics of when the universe's symmetries broke in different ways in different places. Their defining feature is an unimaginable density, a concentration of mass energy that warps space-time around them with ferocious gravity. And it is this ferocity that leads to a radical theory about the first elements. These defects could have acted as cosmic catalysts, ultra-efficient forges for nuclear fusion in the primordial soup. Picture the scene just minutes after the Big Bang. The universe is a hot, expanding plasma of protons, neutrons, and electrons. Now, running through this soup is a cosmic string, a flaw in reality so dense it acts like a gravitational razor wire. Any particle that drifts too close is caught in its intense pull, accelerated to fantastic speeds along its length. In the diffuse plasma of the Standard Model, particles rely on random thermal motion to collide and fuse. It is a slow, chancy process, but along a cosmic string or the face of a domain wall, gravity takes over. It funnels and focuses the nuclear fuel, slamming nuclei together along a one-dimensional line or a two-dimensional plane with relentless efficiency. This is not the gentle, statistical cooking of the standard Big Bang Nucleosynthesis. This is forced fusion, a gravitational hammer driving particles together. The consequences for element production are profound. In the broad, cooling universe, nuclear reactions have only a few minutes to work, and they stop at lithium because building anything heavier requires a triple collision that is astronomically unlikely. But on a topological defect, the rules change. The density and flow of particles are so extreme that rare nuclear pathways could open up. For instance, the triple alpha process, where 3 helium nuclei fuse into carbon, is a process we associate with the hearts of giant stars billions of years later. It requires a very specific, dense environment. The surface of a primordial domain wall or the vicinity of a cosmic string could have provided exactly that environment, a temporary pocket of extreme pressure in the infant cosmos. This means the first carbon atoms in existence might not have come from stars at all. They could have been forged prematurely in these cosmic flaws, billions of years before the first star ignited. This theory suggests the early universe's chemical map was not uniform. It was a tapestry with brilliant, dense threads. Regions crisscrossed by cosmic strings or draped with domain walls would have been local chemical factories overproducing certain isotopes. They might have synthesized tiny amounts of elements like beryllium, boron, or carbon, while also altering the local balance of helium and deuterium. Once these defects eventually evaporated or decayed, cosmic strings might snap and release bursts of gravitational waves. Domain walls might collapse, their uniquely processed material would have been dumped back into the wider universe. What we measure today in ancient gas clouds would be an average, a blend of the quiet background abundance and the exotic output of these spacetime scars. The search for evidence is a hunt for ghosts. We might look for unexplained, hyper-tiny variations in element abundances between different pristine regions of space, a fossilized imprint of where a cosmic string once cut through the primordial cloud. Or we might listen with gravitational wave observatories for the faint, high-frequency hum of strings snapping in the cosmic dawn, the death knell of a catalyst that helped write the universe's first secret recipes. Quantum information was the universe's first language. Before there were particles or forces as we know them, there was a sea of pure potential, a state described not by chemistry or nuclear physics, but by quantum probability and correlation. This theory ventures beyond matter and energy to propose that the most fundamental ingredient in the cosmic recipe was information itself. In the first instance, every particle was entangled with every other, woven into a single, coherent quantum state. This was not a soup of independent ingredients, but a unified, whispering network where the state of one proton was instantly connected to the state of a neutron on the other side of the cosmos. This deep entanglement meant the particles did not behave as separate, classical billiard balls. Their fates were linked by invisible threads of quantum information. As the universe exploded outward, this pristine quantum state began to fray. The process is called decoherence. It is what happens when a perfectly correlated quantum system interacts with its environment, causing those delicate threads of entanglement to snap one by one. The searing heat and blinding radiation of the early cosmos was the ultimate disruptive environment. With each collision, with each interaction with a rogue photon, particles lost their quantum connections and began to behave like independent classical objects. This transition from a quantum world to a classical one was not a silent background process. It was the event that set the rules for the nuclear reactions to follow. Think of it like this. Imagine a vast orchestra where every musician is perfectly in tune with every other, hearing each subtle breath and bow stroke. They can perform impossibly complex, synchronized pieces. This is the entangled early universe. Now, place that orchestra in a roaring hurricane. The musicians can no longer hear each other. They begin to play based only on their own sheet music, losing the magical, emergent harmony. This is decoherence. The moment a particle decoheres, its quantum possibilities collapse into a single, definite state. Its position, its momentum, and crucially, its readiness to interact with other particles become fixed. This directly influences the probabilities at the heart of Big Bang nucleosynthesis. The rate at which a proton and neutron fuse to form deuterium is not just a number pulled from a nuclear physics table. At its core, it is a quantum probability, a calculation of the chance that two particles will overcome their mutual repulsion and quantum tunnel into a bound state. In a highly entangled environment, that probability is not independent. The fact that two particles are entangled means their wave functions are overlapping. Their chances of interaction are inherently linked. They are not searching for each other in a vast, empty arena. They are already holding hands, waiting for the signal to bind. As decoherence proceeds, these handholds are broken. Particles become isolated hunters in an expanding void. The probability of a successful fusion event changes in real time as the quantum connections dissolve. This offers a radically new way to calculate the yields of the first elements. Instead of starting with a classical soup of independent particles at a certain temperature and density, we would start with a specific pattern of quantum entanglement, a cosmic initial condition written in pure information. The expansion and cooling of the universe then becomes a story of information loss, of quantum correlation turning into classical noise. The precise schedule of this decoherence, which particles lost their links first and how quickly, would directly dictate the timeline of nuclear reactions. It could explain why the deuterium bottleneck broke at exactly the right moment, or why the chain toward lithium was so inefficient. Perhaps the lithium problem is not a problem of nuclear physics, but of quantum information. A signature that the entanglement between helium and tritium nuclei decohered just a fraction of a second too soon, cutting off the reaction pathway. This perspective is profound because it suggests the universe's first recipe was not cooked by blind forces acting on dumb matter. It was the output of a cosmic computation, a processing of quantum information into the classical, persistent data we call hydrogen and helium. The light elements are the hard copy, the readout from the universe's first and most monumental calculation. The final theory expands our view to a canvas of infinite possibility. We have explored how the first light elements might have been altered by hidden particles, shifting fields, or quantum chaos. But what if the recipe itself was never meant to be unique? What if the precise 25% helium, the trace of deuterium, and the puzzling lithium are not the inevitable output of a single set of laws, but simply the numbers that happen to win a cosmic lottery? This is the realm of the multiverse and the string theory landscape. It proposes that our universe, with its specific constants and forces, is not the only one. It is a single bubble in a frothing, eternal sea of universes, each with its own distinct physics. In some, gravity is stronger, snuffing out expansion before stars can form. In others, the nuclear force is weaker, preventing atoms from binding at all. The cosmic constants are not fine-tuned by a guiding hand, but are random, local variables set when each universe nucleates from the greater multiversal foam. Our Big Bang nucleosynthesis, then, is not a universal truth. It is a local artifact, a chemical signature unique to our particular bubble. The abundances we measure so carefully are not the only possible outcome. They are simply the outcome that happened here. This perspective transforms the meaning of the lithium problem. In a single, unique universe, a discrepancy between prediction and observation is a puzzle to be solved, a clue pointing to new physics. But in a multiverse, it may simply be a statistical fluctuation. Perhaps in the vast ensemble of all possible universes, the average lithium yield does match the standard prediction, but our universe, by random chance, fell on the lower end of the distribution. We are not seeing a failure of the model, we are seeing the natural variance expected across an infinite cosmic ensemble. The string theory landscape gives this idea a mathematical home. It suggests the possible configurations of the extra dimensions posited by string theory are not few, but astronomically numerous, perhaps 10 to the power of 500 or more. Each stable configuration corresponds to a different vacuum state, a different set of physical laws, and therefore, a different universe with its own version of Big Bang Nucleosynthesis. Most of these universes would be sterile, with constants that forbid the formation of complex structures. A tiny fraction, by sheer accident, would have constants that allow for atoms, stars, planets, and life. We, of course, find ourselves in one of those rare, life-permitting bubbles. From this vantage point, the successful predictions for hydrogen and helium are not evidence of a single, perfect theory. They are a form of cosmic observation bias known as the anthropic principle. We can only measure the light elements in a universe where the constants allowed those elements to form, and where those elements subsequently allowed for observers to arise. The recipe we have deciphered is not the master blueprint, but a single page from one volume in an infinite library. This does not make the quest for understanding futile. Instead, it reframes the goal. Scientists working within this framework ask a different question. Not, why do the constants have these exact values, but given that we exist in a universe that produced observers, what statistical predictions can we make about the constants we should expect to measure? Could the specific abundances of helium and deuterium be the most probable outcomes within the subset of life-allowing universes? The search becomes one for statistical correlations in the landscape. The light elements, then, are more than relics or clues. In the multiverse view, they become our cosmic address, a string of numbers that identifies our particular bubble in the froth of reality. They tell us not how the universe had to be, but simply how it is in this one rare and precious corner of the limitless whole. From the solid, triumphant predictions of the standard model to the wild frontiers of cosmic strings and bubbling multiverses, this journey reveals a stunning truth. The first 3 minutes were not a simple, predictable bake-off. They were the universe's ultimate laboratory, a place where every extreme of physics was tested and recorded in the only permanent record we have, the atoms themselves. That 25% helium is more than a number. It is a cosmic signature, a line written in the autobiography of reality, detailing encounters with ghostly neutrinos, decaying particles from the dark sector, and perhaps even the vibrations of strings from a time before time. We have moved from the certainty of nuclear physics into a realm of breathtaking speculation, where the recipe for hydrogen and helium becomes a key to unlock doors we are only beginning to imagine. Each theory, from the lumpy inhomogeneous cosmos to the gravitational hammer of primordial black holes, offers a different lens on that foundational moment. They remind us that our origin story is still being written, with every observation of a pristine gas cloud or a distant quasar are adding a new word, a new sentence. So, the next time you look up at the night sky, remember that the vast, silent expanse began in a frenzy of creation so precise that its echoes determined the fate of galaxies and the potential for life. Which of these 30 theories about the universe's first light captivated you the most? Was it the idea of a mirror world cooking its own elements alongside ours, or the violent turbulence of a supercooled quark soup? Share your thoughts in the comments below, and if you want to continue exploring the deepest mysteries of the cosmos, be sure to subscribe. Our journey into the unknown has